Salam, peace be upon you. Before we step into part 8, let me weave the certified thread so far, in one tight paragraph, with no new ideas smuggled in. Episode 14 is locked as a compiler, not a story. We have sealed the layer tags so structure grammar stays separate from becoming and meaning. We have separated framework completeness from implementation results. We have installed honest correspondence typing so we can relate to other frameworks without fake derivations. We took the extraction oath, compile certified structure, or issue refusal with audit. And we froze public meaning. Only differences in phi are speakable. Absolute phi is silent. Now listen carefully, because part 8 is where most frameworks commit their first quiet crime. They smuggle in space. They smuggle in coordinates. They smuggle in a background container, some invisible stage. And then they pretend they didn't. And once you let that stage in the door, the whole cathedral becomes a theater. You can still write beautiful equations. You can still tell convincing stories. But you no longer know which parts you earned and which parts you assumed. You no longer know what is public structure and what is inherited furniture. So part 8 is severe. Part 8 is the security checkpoint at the entrance of the compiler. It asks one question. What exactly is allowed to enter the machine? And today I certify the raw input object. Not a universe, not a space-time, not a coordinate chart, not a metric, not a field defined on space. The raw input is simpler and more honest. The raw input is a comparator graph. Events plus comparison edges inside licensed windows with passports attached. Nothing else is allowed through the door. Let me build this slowly, in a way you can feel. Imagine two strangers meet in a dark room. They cannot see the room size. They cannot see the walls. They don't know if the room is a cube or a cave. They don't even know if there is such a thing as left and right beyond their own bodies. But they can do one thing publicly. They can compare. They can say, when I touch this spot and you touch that spot, the two readings differ by this much. Or, these two moments in our protocol produce comparable marks on the ring. Or, this detector click and that detector click stand in a measurable relationship under the same passport. That is public. Not because it is grand, because it is checkable. Now watch what absolute thinking tries to do. Absolute thinking says, fine, but where are those events located? What time did they occur? What is the distance between them? What coordinate are they at? And part 8 says, you do not get to ask that yet. Not because we deny geometry, but because we refuse to pretend we already own it. In episode 14, geometry is not input. Geometry is an output possibility, derived later as a readout, if the extracted structure earns it and survives invariance. So we begin with a graph, and I'm going to say graph the way a child could understand it. A graph is dots and lines. The dots are events. The lines are comparisons. That is all. No grid behind it. No map paper beneath it. No x-axis, no y-axis. Just dots and lines. But there is something that makes our graph different from a child's drawing. Every line carries a measurement claim, and every claim lives inside a window with a passport. So the graph is not just topology, it's audited topology. It's public comparability encoded as a structure that can be hashed, logged, repeated, and attacked. Now let me state the core certification of Part 8 as plainly as I can. The raw data object for episode 14 is a comparator graph, spoken formally but gently. A set of events plus a set of directed or undirected comparison edges where each edge records an admissible comparison of 5 differences inside the licensed window, together with a passport describing how that comparison was obtained. And the anti-smuggling clause is absolute. No coordinate fields, no metric, no background container, no implicit space-time scaffolding. If any of those sneak in, the input is rejected. Now you might ask, but how can we do science without coordinates? How can we talk about anything without space and time? And this is where I need you to feel the difference between a compiler and a story. A story begins with the stage. A compiler begins with the symbols it can verify. We do not begin with space. We begin with comparisons. And if space is real in a public sense, it will emerge later as an invariant structure that makes the comparisons maximally coherent across windows, without ever being imported as a primitive. That is the discipline. Now, I want you to see why this matters across scales, not just in some abstract philosophy. At the quantum scale, what do we really have? We have cliques, counts, correlations, interference fringes, comparisons between events under controlled protocols. The apparatus gives you relational patterns, not the particle's absolute position in space as a primitive gift. At the biological scale, what do we really have? We have sequences compared to sequences, expression levels compared across conditions, activation patterns compared across cell states. The space of the cell is not given to you as a Euclidean box. What you actually record are relational differences. This marker is higher than that marker under this condition. This pathway signature differs from that signature under that condition. Comparisons. At the cosmological scale, what do we really have? We have redshift comparisons, brightness comparisons, angular separations, timing differences under instrument protocols. Even the sky map is not space itself. It is a relational encoding of measurements stitched together by conventions, calibrations, and windows. So across scales, public science begins as a web of comparisons. Part 8 simply refuses to lie about that. Now let me define the comparator graph more carefully in spoken terms, because we will use it again and again. The nodes, the dots, are event tokens, not points in spacetime, not particles, not moments, just event tokens, places where a comparison could be made. Each node has an identity inside a window passport, how it was indexed, what instrument lineage it belongs to, what masking and excision rules apply. The edges, the lines, are comparator edges. Each edge says, between node I and node J, we have an admissible comparison of phi differences, recorded under this passport. Sometimes the edge carries a value like delta phi between I and J equals this, with uncertainty epsilon. Sometimes it carries a distribution, because the instrument produces statistics. But the key is, whatever it carries, it is still only a comparison claim, nothing absolute. And every edge is tagged with conditions that make it public: window boundary, calibration lineage, coherence checks, identifiability rank, and max ceiling, uncertainty lineage. If you cannot attach these, the edge is not admissible. Now I'm going to say something that might sound like I'm repeating part 7, but this is where it becomes an engineering rule. Because public meaning is differences only, the raw data object must not contain absolute anchors. So even if your instrument reports an absolute phase reading, the compiler refuses it as raw input unless it can be converted into certified differences under the passport. That is why the comparator graph is the correct input object. It matches the public meaning rule by construction. Now I will name the gates of part 8, and I will weave them into a story you can carry. Gate 1 is the domain gate, DOM. This gate asks, Are the nodes and edges typed to certify domains? If someone hands you a graph where some nodes are events, but nobody can say what window they belong to, or what boundary conditions apply, or whether the data is aliased, then the graph is not a public object. It is a fiction. DOM insists. Every node lives in a declared window domain, and every comparison edge is admissible only if it connects nodes whose comparability conditions are defined and auditable. Gate 2 is the well-formedness gate, WF. WF asks, is this input actually a comparator graph, or is it a disguised geometry? A well-formed comparator edge is a statement of comparability. These two event tokens are compared under procedure P, yielding a difference record. An ill-formed edge is, these 2 points are distance 5 apart. That is geometry smuggling. WF is ruthless. If the input contains coordinates, metric entries, distances, or any primitive geometric scaffolding, it fails. Gate 3 is the passport dependency gate. This one is simple and brutal. No passport, no input. If a node has no passport lineage, it cannot enter. If an edge has no passport lineage, it cannot enter. If a graph cannot be traced back to a window license and a measurement procedure and a calibration lineage, it cannot enter. Because in episode 14, public claims are not just claims. They are claims with paperwork. And the paperwork is not bureaucracy. It is the only thing that separates public science from private storytelling. Gate 4 is the anti-smuggling gate. This is the one that catches the clever crimes. Because many people will not smuggle geometry directly. They are too smart for that. They will smuggle it indirectly. They will give you an adjacency matrix that secretly encodes distance. They will give you a neighborhood radius parameter. They will give you a kernel that assumes Euclidean closeness. They will give you smoothness priors that are secretly metric assumptions. They will say, we only connect nodes within epsilon, and epsilon is a distance. They will say, we interpolate along the shortest path, and shortest is a metric. They will say, we assume local linearity in coordinates, and coordinates are geometry. The anti-smuggling gate scans for all of this. It asks, does any part of the input require a background container to even define its meaning? If yes, it is rejected. Now, I want you to feel why this is not a petty purity test. This is what keeps episode 14 from silently turning into the very thing it claims to replace. If you let geometry in as input, you are no longer extracting geometry. You are assuming it. And then later, when you derive space, you will have derived the stage from the stage, a perfect circle, a mythology with equations. We refuse. Now, I will say the compulsory toolchain line, because every part must say it somewhere, and I want it inside your bones. Licensed window, passport and coherence and identifiability, Nmax and uncertainty, local lift, cuts if needed, excisions, certified domain D, A equals D phi tilde, finite jets up to Nmax, invariance collapse, topology and defects, invariant bases, stability and entities, scale stratification, escape test, handoff. Part 8 sits at the beginning of that chain. If we corrupt the input, everything downstream is corrupted. So part 8 makes the input object explicit and auditable. Now let me give you the carrying picture. I want you to imagine you are building a judge's courtroom for science. The comparator graph is the evidence bag. Every node is an evidence item with a tag. Every edge is a documented comparison between two items. The passport is the chain of custody. If chain of custody is broken, the judge throws it out. If someone tries to sneak in a forged document, geometry smuggled as obvious background, The judge throws it out. That is part 8. Now let's talk about the prediction of this part, because we do prediction without dynamics. The prediction is not what will happen tomorrow. The prediction is what must be true of any certified output if part 8 is correct. Here it is. Different instruments that yield compatible comparator statistics will yield compatible certified structures, even if those instruments do not share any coordinate system or background geometry. If the raw input is truly comparator only, then the compiler does not care whether you used photons, electrons, pressure waves, neural spikes, or survey catalogs. If the comparator graph statistics match under passports, the extracted invariants should match. So part 8 predicts a kind of instrument humility. The structure is not owned by a coordinate system. It is owned by invariants extracted from comparisons. And now the falsifier. Here is what would break part 8 cleanly. If someone can show that the necessary certified structure cannot be extracted from comparator data plus passports, and instead requires hidden primitives, metrics, coordinates, background containers, that cannot be represented as comparator graph fields, then the comparator graph is not a sufficient raw data object, and the framework must be extended or it fails. Even more bluntly, if any extraction step truly requires a metric as primitive input, then episode 14's input contract is violated. That is the falsifier. Not I feel coordinates are needed, but here is a public structure claim that cannot even be stated or tested unless we assume a background metric as primitive. If that happens, we log it, we face it, and either we justify a controlled extension or we accept failure. No hiding. Now let me bring this alive with examples across scales, but I will keep them within the firewall. No dynamics, no stories of evolution, no meaning claims, only public comparability. Example at a human scale. 2 thermometers. Imagine thermometer A and thermometer B. They are built differently. They have different internal scaling. They might even use different physical principles. If I demand absolute readings, they will fight. But if I build a comparator graph, I connect events like measurement of room now compared to measurement of ice water, compared to measurement of boiling water, all with passports. Now the graph can carry differences and ratios that both instruments can certify, even if their absolute scales differ. The certified structure is in the comparator relations, not in an assumed absolute temperature coordinate. Example at an imaging scale. A camera sensor. A camera does not measure absolute brightness in a platonic sense. It measures differences under exposure settings, calibration, noise floors. So a comparator graph for an image is not pixels located on a plane in space. That is geometry smuggling. The raw object is detection events compared under sensor adjacency that is itself a hardware-defined stencil class, logged in the passport. And here is the key. That adjacency is not distance in space. It is which sensor elements are compared under the instrument's stencil. We can say this pixel and that pixel are compared because the sensor compares them. That is allowed because it is instrument lineage, not universal geometry. But we cannot say these pixels are adjacent because space is continuous. That is smuggling. Example at a neural scale, electrode recordings. If you record neural activity, your raw data is not a field over brain space. That is already interpretation. The raw data is a set of channels with comparisons. This channel differs from that channel under this filter, under this noise model, within this window. Again, comparator graph. Example at a cosmic survey scale, galaxies. A survey gives you detections, fluxes, redshifts, angular separations under calibration. The raw object is not galaxies in three-dimensional space. That is a derived interpretation. The raw object is comparison relations under instrument and analysis pipelines, which can be encoded as a graph. Later, geometry may be compiled as a readout if it is earned, but it is not input. So you see the power. One raw data type across scales, dots and lines, passports and gates. Now I want to confront the most seductive counterargument. People say, but don't we at least need nearness to define derivatives? And the answer is, we need certified locality, not assumed geometry. Locality in episode 14 is not small distance in space. Locality is comparability neighborhoods defined by the window and the sampling stencil, with explicit boundary conditions and coherence tests. In other words, locality is a property of the comparator graph plus passport, not a property of a background manifold. If your instrument compares event A to event B reliably, that is an edge. A neighborhood is defined by edges, not by coordinates. Later, if the graph's adjacency patterns are consistent in a way that supports a manifold-like readout, we may compile that as geometry. But we do not assume it. This is the whole point. Now we must include an invariance stress test in part 8. Here is the one that fits perfectly. Stress test, relabeling invariance. Take your comparator graph. Relabel the node IDs. Rename every node arbitrarily, without changing the adjacency structure or the edge data. The certified outputs must not depend on the labels. If your extraction depends on node names, you are not extracting structure, you are reading a spreadsheet header. So we require permutation invariance. Changing the naming of events cannot change the certified structure. Another stress test. Constant shift invariance from part 7. If edge values represent phi differences, adding a constant to phi everywhere does nothing to differences. The raw objects should be stable under that counterweight shift. If your raw input secretly contains absolute phi anchors, it will fail. And the third stress test, lift class invariance. If edge data depends on a specific unwrapping of the circle, we test it under alternative lifts. Any dependence is revoked. Those are stress tests. They are the compiler's immune system. Now I will say the carry line of part 8, because you need one sentence that can survive in your pocket. We don't begin with space. We begin with comparisons. Hold that. Because if you hold that, you will immediately detect the hidden geometry that almost every theory smuggles in as obvious. Now I will do the thing that makes episode 14 different from inspirational talk. I will define the audit artifact. Part 8 produces a specific ledger entry for the input object itself. For every admissible comparator graph, we write 1, a graph hash, so the object has a public identity. If someone alters one edge, the hash changes. No silent tampering. 2, the adjacency structure, recorded explicitly. Not assume nearest neighbors, but these are the edges. 3, the sampling stencil class. This means, what rule produced these edges? Instrument adjacency? Random sampling? Cross-correlation pairing? The stencil class is logged because it defines what counts as local comparability inside the window. And crucially, it is described without assuming geometry. It is described as an operational pairing rule. 4. Instrument lineage. Which sensors, which calibration certificates, which processing masks, which excisions. Passport dependency is not optional. 5. Smuggling checks. A checklist that answers, did any field in this input object encode metric assumptions? Did any parameter require coordinates to interpret? Did any kernel imply Euclidean distance? Did any smoothing assumption hide a manifold? Pass or fail is logged. And if anything fails, we don't patch it with rhetoric. We issue refusal. Now the refusal certificate for part 8 is also explicit. Refusal is not "we don't like your data." Refusal is input rejected at anti-smuggling gate because it contains a distance field not representable as comparator edges plus passport fields. Or input rejected at passport dependency gate because edge lineage is not reconstructible. Or input rejected at well-formedness because it contains coordinate primitives. Refusal is categorized, logged, and archived. That archive is part of scientific progress because it shows exactly where people keep trying to import forbidden primitives. Now I will state the revocation clause because the drift killer must be sharp. Any input that implies metric, coordinates, background containers, or any geometry as primitive, explicitly or implicitly, must be rejected or revoked immediately. If an input passes and later a smuggling leak is detected, all downstream outputs derived from that input are revoked, the provenance chain is marked contaminated, and the case is sent to the negative archive with a precise failure classification. No exceptions. Because if we allow exceptions here, the entire program becomes a stage play. Now let me end by tying part 8 back to the promise of episode 14. Episode 14 does not describe reality. It specifies the conditions under which reality can be described at all. Part 7 told us what meaning must look like for public science. Differences only. Part 8 tells us what data must look like for public science. Comparisons only. If you want to enter the compiler, you do not bring me a universe. You bring me a comparator graph with passports. Dots and lines. Edges that represent comparisons. No hidden map underneath. And if you feel the seriousness of that, you should also feel the liberation. Because once we stop assuming the stage, we finally earn the right to extract it. Not by declaration, not by tradition, not by inherited metaphysics, by procedure, by invariance, by audit. Part 8 complete. The raw data object is certified. Comparator graph. No geometry smuggling. And the carry stays simple. We don't begin with space. We begin with comparisons. Always. Peace be upon you.